Yeah, today we're moving on to 6.2a, simplifying radical expressions. So everything we've done so far is just kind of talking about the laws of exponents and trying to make sure that we're ready to actually kind of make this jump. I want you to understand before we start that radical expressions and exponents, they're kind of in the same family. They're actually inverses of one another. So I want to work one little example here, actually a couple examples, just to kind of get us started, and then we're going to talk about this. This is going to be a little bit of a long video just because there's a lot to cover here. But our mission is I can multiply and divide radical expressions and simplify the product or quotient. So first, again, I want to just think about the fact that radicals and exponents, they are kind of in the same family. So if I had the square root of 3 and I were to square that, okay? First of all, when we say square root, I want you to understand that even though it's not there and we typically don't write it in there, there is actually a 2 right there. For example, if we had something that was cube root, then we would put a 3 right there. If it was a fourth root, we would put a 4 right there. So this is our index. It kind of tells what root we're taking. Again, typically we don't put a 2 there, but it's just kind of understood that if that's not there, that it is a square root. So we're taking the square root of 3 and we're squaring it. Now again, just what we learned about exponents is this exponent right here is telling me, right? This exponent is telling me that I'm going to repeat this base twice. Okay, so really what you're doing in essence is you're taking the square root of 3 times the square root of 3. Okay, now the square root of 3 times the square root of 3 is in fact the square root of 9. So 3 times 3 is 9. And then the square root of 9 ends up just giving us 3. So you kind of see that these two operations, they undo one another, okay? So if I square a square root, it actually kind of just cancels all of that out, and I'm just left with the number 3. And so that is very important as we kind of get into this today. The other thing that we need to talk about is we need to talk about simplifying square roots, okay? We've already kind of did this, but I want to walk through one example again. So let's take, for example, the square root of 50. Okay, if I were to ask to simplify the square root of 50, then I've got to think about the fact of, well, I've got to see if there's any perfect squares in here. Okay, so real quickly, I'll just go over what we've already went over before, but just as a refresher here. So if I make me a little perfect squares table, for example, we'll go through 7. I go ahead and just kind of fill this out. So 3 squared would be 9, 4 squared would be 16, all the way down to 49. And so I'm looking through this list and I'm saying, okay, is there a perfect square maybe that's hiding in this square root of 50? Okay, and I go through my list. Obviously, I want the biggest number. So 49 does not go into 50. 36 does not go into 50. But right here, I can understand that 25 will go into 50. So what I'm going to do here is I'm going to rewrite this as 25 times 2. And really, I want to go even a step further and say that 25 is the same thing as 5 squared times 2. You remember we said anytime that we square a square root, it actually undoes that, and it actually allows it to come to the outside, okay? So what I want you to notice is, and again, I'm going to write this one more time, just so that we can kind of get this idea here. This is really the same thing as 5 times 5 times 2. So anytime I have a group of 2 like this, then that number can come to the outside, okay? And anything that I don't have 2 of is going to have to stay on the inside. So actually what ends up happening here is the square root of 50 ends up being simplified as a final answer here of 5 radical 2. So again, this is all review. It's kind of what we've already did before, but it's very important because it's going to help us as we work through these examples. So let's go ahead and just go right into one example here. So we're going to call this one number 1. And you're going to notice some things here. We not only have a number in here, but we also have some variables as well. Yes, you knew us math people, we had to throw in some variables. What I want you to notice though is that I can go ahead and I can split this out into 2 parts. So here's what I'm going to do just to kind of show you what's happening here. I could also rewrite this as the square root of 75 times the square root of x to the 8th, okay? And we're going to kind of take this in separate pieces and go a couple of different directions with it. And so the square root of 75, again, I would kind of look at my square roots table. I also want to show you something else here. We could look at maybe a factor tree. And so let's think about what prime numbers would go into 75. And right off the bat, when I see this 5 at the end, I know that pretty much I know 5 is going to go into that, right? So 5 times what gives me 75? Let's see, that would be 15. And now I'm just thinking again about prime numbers that may come out of this. So 5 is just going to keep coming down. That's a prime number. What are the factors of 15? Well, the factors of 15 is 1 and 15. That doesn't really help me. But I also have 5 times 3, right? And now I have nothing but prime numbers down here at the bottom. So I want you to understand that this is prime factorization. Okay, this is getting down to nothing but prime numbers, kind of breaking the number 75 down. So this is another way that you can do what we did a while ago with the square root of 50. So now let's just think about what we really have. We have the square root of 5 times the square root of 5 times 3. That's the same thing as the square root of 75. And what did we say in our previous example? If I have a group of 2, I can go ahead and pull those out. So I have 2 5s here, which means I could go ahead and pull a 5 out to the front. I'm going to leave a little bit of room, and I'm going to go ahead and put the square root of 3. It can't come out and play because it only has one particular part here. So now let's look over here at what we have with the square root of x to the 8th. Remember we said that this is a square root, even though it's not really there. We don't usually write it there. It's understood that there is a 2 right here, okay? So what I want you to think about is if I had, and let's just expand this out, okay? X to the 8th is the same thing as x times x times x times x times x times x times x. Wow, 1, 2, 3, 4, 5, 6, 7, 8. There they are, okay? And what do we say? As long as we have a group of 2, then I could pull those out, okay? So let's just think about how many groups of 2 I really have. I've got one group of 2 here. I've got a group of 2 there. I've got a group of 2 there, and I've got a group of 2 there. How many groups of 2 do I have? Well, I actually have 1, 2, 3, 4 groups of 2, which means, watch this, I can pull out x to the 4th because I had 4 of those x groups, okay? And notice what happens. This is my final answer. This is done, okay? I'm finished. What I want you to see is really all you have to do is just take the exponent that you have here. This is x to the 8th. And divide it by 2, and you will notice that I get exactly 4 groups out, okay? Let's just take one more little quick example just so that you can kind of see what happens if that doesn't come out even, okay? So let's think about this. If I had the square root of x to the 9th, well, again, how many groups of 2 could I get out of that? Well, if I take 9 divided by 2, and this is a really simple example, that will go into that 4 times evenly, but I will have a remainder of 1, okay? So I could get 4 groups of 2 out, but I'm still going to have 1 left over. So let's think about what that really looks like. I'm going to have x to the 4th, but I'm still going to have 1x that's going to be left over in the inside, okay? So this right here, the square root of x to the 9th, is the same thing as x to the 4th square root x, okay? So we're going to actually get into another example that'll kind of show that as well, but I wanted to just show you that up front so that you kind of see what you need to do. Again, basically all you need to do is just take this exponent that's underneath the radical and divide it by the index, whatever that index is, all right? Let's look at another example. I think it'll help us. This time we're going to add in some multiplication. So number 2, we have 3x squared times 21x to the 3rd, okay? So first thing we want to do is we want to go ahead and do this multiplication. Again, we just kind of take the coefficients, which would be the numbers in front of the variables, and let's do those first. So I'm just going to make one square root symbol. 3 times 21 is 63. And then I have x squared times x to the 3rd. Now you kind of understand why we went over all those exponent rules, right? So when I multiply exponents, I actually add them. So x squared times x to the 3rd is going to be x to the 5th. And again, we're going to do the same thing we did a few minutes ago. We're going to kind of just split this into 2 parts. So I've got the square root of 63 here. I've got the square root of x to the 5th over here. Let's deal with this square root of 63. Again, what numbers will kind of go into 63? We know that 3 will go into 63, and it will go into 63 21 times. And again, you could use a calculator to kind of help you with those calculations as well. 63, 3 times 21, and then the 3 is a prime number. And then what are the factors of 21? Let's see. So 1, 2 won't go into 21, but 3 will go into 21 7 times. And now I have nothing but prime numbers down here, which means that that is as simple as it gets. 3 times 3 times 7. And let's see, anything that we have 2 of, I can bring out. So I have 2 3s, which means that I could rewrite this as 3 radical 7. You notice I'm leaving a little bit of room here in case I have some variables that may come out. So let's just think about this again. Remember that there is a 2 right here. So I'm going to do it both ways, just so you kind of see it. We've got x times x times x times x times x. And again, the reason I wouldn't want you to have to do this every time is what if this was x to the 10th or x to the 20th? You wouldn't want to write that out a bunch of times, right? So here we're just looking for groups of 2. So I see one group of 2, 2 groups of 2, but I have one that is left over. You see that right here? I've got one that's left over that kind of don't have a partner for the dance, okay, if you want to think about it that way. So really what I can do here is I can pull out 2 groups of x because I've got 2 groups of 2, right? But one of this other x has to go underneath this radical with the 7. It can't come out because it doesn't have a partner. Again, just thinking about this as all I really am doing is I'm just taking this 5 and I'm dividing by 2. So 5 divided by 2 will be 2 with a remainder of 1. Okay, so 2 come out, 1 stays underneath. Hopefully you're getting the idea of what we're doing here. And a lot of this is just repetitive motion that you'll keep doing over and over and over again. All right, so let's look at number 3, which is a division problem. So number 3, we have the square root of 350 x to the 7th over 2x, okay? So you notice up above here, I actually took a problem that was already kind of together and I split it into 2 parts. Well, you can also do that same thing, but you can actually put all of this underneath one radical. And in this case, it really does help you to be able to see what's kind of going on. So let's take this same thing, and I'm going to put it all under one radical like this. Boy, that's a huge one, right? What I'm going to do is I'm going to put all of this information under one radical, and you're really going to see why here in just a second. So you have 350 x to the 7th over 2x. Now, right away, hopefully, you're starting to see maybe why we did that, because we're going to see how truly simple this is going to get here in just a second. What I want you to notice is you have a 2 down here as a coefficient, and you have a 350 here as a coefficient. So right away, we know that we can actually simplify this fraction a little bit. So we're going to go ahead and do that. I'm going to move my work down here. So I'm going to end up with 350 divided by 2 would be 175, okay? I want you to see that, okay? So that kind of went away. This become 175, right? Now notice here I have 1x here and I have 7 x's on the top. So I have 1x here, 7 on the top, which means that at least one of these will cancel out, and that will actually make this a 6, okay? So notice I have everything on the top and nothing on the bottom. So I no longer have a fraction. This big thing here that was really just like, oh my goodness, what am I going to do, now has really been reduced to 175 x to the 6th. You can see how now that this becomes just like the other problems I said already, that it's going to kind of be repetitive motion, okay? So again, we could kind of look at this and look at this as 2 separate parts. So square root of 175 times the square root of x to the 6th. And let's just take it as individual pieces. Now, again, if you're thinking about, I'm going to go back to the perfect squares list for just a second. Think about what perfect square may go into 175. One of the ones that come to mind right off the bat is 25, right? So 25 times, let's see. 7 would give me 175. And then 25 again could be broken down into 5 times 5 times 7, right? So this would be my prime factorization for the square root of 175. So I'd have 5 times 5 times 7. Again, if I've got a group of 2, I can go ahead and bring that out. So that means I'm going to end up with 5, and I'm going to leave a little bit of room and put radical 7. Okay, now I'm going to go ahead and start resolving this one, which is x to the 6th. And this time, again, we're just going to use division. So we have 6 right here divided by 2, which is my index, and that would equal 3. That means 3 groups of x can come out of this radical, and I'll have nothing left over, which means there won't be any x's inside or underneath my radical. So that means that I'm going to have x to the 3rd that is going to come out. So this, ladies and gentlemen, would be my final answer for that particular problem. Now let's move to the last one, which is going to be one of the most difficult ones, but it's okay because I'm pretty confident that we can figure this out, okay? So I'm going to go to number 4, and now we have the square root of x over the square root of 3. Now, you may think immediately, well, let's just do what we did with the last problem. Let's go ahead and make it one big radical, and we could do that. What I want you to see is it's not really going to help me at all. There's nothing really that's going to cancel out. There's nothing that's actually going to do for me. So really, I'm just going to end up splitting it right back out again because it's not really going to help me. There's no x's on the bottom, so I can't cancel anything out. There's nothing that 3 will divide into up here in the numerator. So again, I'm kind of just left at a point where it wasn't really any use for me to do that at all. Okay, and you kind of got to look at your problem and see if you can see things that are divisible, and if there are, then maybe you can make this a little bit simpler on yourself. But in this case, this doesn't really help me, okay? So I'm going to go ahead and just go back to my original problem, square root of x over square root of 3. And here's what I want you to understand is that it is absolutely, totally, 100% illegal, all right, for me to have a radical on the bottom. I cannot have a radical on the bottom. And so in order to get rid of this, I have to do something called rationalize. I have to rationalize this square root of 3. And the way we do that is a lot like what we did with conjugates and complex numbers. Again, let's go back to our original example. Our original example was if I could take the square root of 3 and I could square that, then that becomes just a regular 3, and now all of a sudden I don't have that to happen. Well, what do I need to multiply the square root of 3 by in order to get 3? Well, again, remember that this is really the square root of 3 times the square root of 3. So if I could just multiply by the square root of 3, I could get rid of that radical sign. Well, guess what? We can do that. The only caveat is if I multiply the bottom by the square root of 3, guess what? I have to also multiply the top by the square root of 3, okay? So notice what happens here. On the top, when I have fractions that I'm multiplying, I just multiply straight across. So the top simply becomes the square root of 3x, whereas the bottom is the square root of 3 times the square root of 3, which just simply becomes 3. Ladies and gentlemen, this is my most simple answer. Now, I may be tempted to say, well, maybe I could cross out these, but I want you to understand that the square root of 3 and 3 are 2 totally different numbers, okay? So we cannot just cross those out. This is actually in simplest form. This is as simple as this particular answer can get because there's nothing else that we can really cancel out, okay? All right, so hopefully this has been helpful. Again, if you run into one of these like number 4, then you're going to need to multiply the bottom by whatever you have, and then that will eliminate that square root for you, okay? So if you have any problems or issues, please reach out to us. We'd be glad to try to help you with those and get you the help that you need in order to make you to be successful, okay? Have a good weekend, and we will see you again next week.